Members, this is Dickson Katamba, and I'm going now to present the linearity property of the Laplace transforms. So the linearity property of the Laplace transforms ascertains that the Laplace transform of a linear combination of two or more functions is a linear combination of the individual Laplace transforms of each of those functions. So here what they are meaning is that if you have two Laplace transforms uh, expressed in one linear expression, let's say you're adding two functions or subtracting them, and you wanted to find the Laplace transform of the whole of that expression, it will be the same as getting the Laplace transform of each of the functions in that expression, and then you add or subtract those Laplace transforms. So what you get after adding the individual Laplace transforms or subtracting them will be the Laplace transform of the whole of the expression. So it can be demonstrated here below that if we have a function f of t and another function g of t, which are having Laplace transforms, capital F of s and capital G of s respectively, and for a and b being constants, then the Laplace of this expression, where you're having a times f of t plus b times g of t is equal to a times the Laplace transform of f of t plus b times the Laplace transform of g of t. So that is basically the expression for the linearity property of the Laplace transform. So we can go on and prove this in the next slide. So they have given us that capital F of s is equal to the Laplace transform of f of t, and we know that the Laplace transform of f of t is equal to integral from 0 to infinity exponential negative st dot f of t dt, and then g of s is equal to the Laplace transform of g of t, and this is equal to integral from 0 to infinity exponential negative st dot g of t dt. And then having the expression that the Laplace transform of the constant a times f of t plus the constant b times g of t is equal to integral from 0 to infinity exponential negative st dot the expression then times dt. We know that this is the expression for getting a Laplace transform of any function. So we can expand this as we know from calculus that we can separate these two here. So we can have the integral from 0 to infinity exponential negative st dot af of t dt, then plus integral from 0 to infinity exponential negative st dot b g of t dt. Since this is common, so it has to multiply each of these two functions. So here we see that a and b are constants, so we can factorize them out as we have here, and then we remain with what we see here, the integral from 0 to infinity exponential negative st dot f of t dt, and then integral from 0 to infinity exponential negative st dot g of t dt. So we see that this is equal to the capital F, the Laplace transform of f of t, and this is equal to the Laplace transform of g of t. So we can literally replace those with their Laplace transforms, and then we can conclude that the Laplace transform of this expression is just equal to getting the constant times the Laplace transform, then plus the constant here times the Laplace transform of g of t, which is g of s. So This is the linearity property. And if at all we had a minus here, similarly we would be having a minus here. So that is it for the Laplace transform. So we can proceed to see an example. If we are told to find the Laplace transform of such an expression, negative 3 plus 7 exponential 3t minus 6 sine 2t. So here we shall write that the Laplace transform of that expression is equal to the Laplace transform of each of the functions in the